Welcome back to the deep dive. We're here again to really crack open some complex tech stacks.
Yeah, get right into the fundamentals.
Today, we're focusing on something you almost never see, right? It's the hidden machinery, the gritty data engineering work that has to happen before any AI model can actually do anything useful.
It really is the engine room. You hear so much about the latest LLM, the fancy algorithms,
Mm-hmm.
but honestly, the success or failure of any big data project, it really comes down to like three core things.
Yeah.
Transforming that raw information, making sure you can access data super fast, and this is a big one, turning those messy, unstructured documents into actual knowledge.
Right, the classic garbage in, garbage out problem. So this deep dive is about the system that stops the garbage getting in, making sure only gold goes into those expensive models.
Pretty much.
Our mission today, then, is a shortcut. We want you to understand these three pillars: feature engineering, SQL optimization, and these new agent workflows, and what they mean for speed and cost.
Exactly. We're looking at the strategic bottlenecks, the things that really dictate whether stuff works at scale. This isn't just about, tweaking a model for 1% better accuracy.
More fundamental.
It's about making the whole thing possible. If that data foundation is shaky, forget real-time insights. And your cloud bill, through the roof. You need a deep foundation to build high.
Okay, let's dive in. Section 1, the foundation. We're starting with feature engineering. You called it the overlooked step.
Oh, absolutely. It's the silent majority of the work,
Yeah.
easily. Data science itself, it pulls from everywhere. Economics, stats, computer science, domain knowledge.
Right.
And the whole point is to get actionable insights from all this raw, messy information out there. Sensor data, clicks, documents, whatever.
And if you look at the whole life cycle, there are usually, four main phases?
That's the standard model, yeah. Phase 1, data prep, which is feature engineering. Phase 2 is modeling, building the actual AI.
Then deployment.
Phase 3, deployment, getting it live. And phase 4 is insight generation, where it actually does its job, makes predictions, helps decisions.
Okay, but here's the strategic gap you mentioned.
What?
Phases 2 and 3, modeling and deployment. They get all the attention, right? All the hype.
That's where the headlines are.
Yeah.
But that first step, transforming raw data into something predictive, feature engineering, it's constantly undervalued, overlooked.
It's like focusing on the shiny race car, but forgetting about the engine tuning and the fuel quality.
Exactly. It's classic infrastructure blindness. We love the new, shiny algorithm, but forget the pipes that feed it. Feature engineering is the absolute prerequisite. You could have the best GPT model in the world, but if the data you feed it doesn't actually describe the problem well, it's useless. If the features aren't predictive, the model just can't learn properly. It won't work on new data.
So let's pin this down. Feature engineering. What exactly is it? Are there other names for it?
So feature engineering is basically the art and science of taking raw data points and transforming them into features that can predict something. You'll hear people call it building data pipelines,
Okay.
especially in big companies. Or the old term, ETL extract, transform, load. Sometimes you hear variable transformation or data transformation.
But whatever you call it. ETL pipeline. The goal is the same.
One goal, transform the data so the AI model can make the best possible predictions from it, maximize its capability.
Got it. Making it understandable for the machine.
Exactly. Mathematically digestible, structurally relevant. So let's look at some core techniques, a really common problem. What do you do with categories, like text?
Right. Technique 1, dummy variables. Or one-hot encoding. So if my data has a column with red, blue, green, the model can't just do math on red, can it?
Nope, that's the core problem. Most machine learning models, especially the traditional ones like regression or SVMs, they live in a world of numbers. Continuous or discrete numbers, they measure distance, relationships, mathematically.
Can't run gradient descent on the word blue.
You got it. So one-hot encoding takes that text column and turns it into numbers, binary numbers.
How does that work?
For every unique value, red, blue, green,
Yeah.
you create a brand new column. So you'd get an is-red column and is blue and is green.
Okay.
And if a particular row originally said blue, then in the new columns, is blue gets a 1, and is red and is green get a 0.
Ah, so it's like a set of switches, on or off for each color.
Exactly. A sparse binary matrix. Now the model can handle it. It can assign a weight to blueness.
And you haven't lost the information, you've just changed the format so the machine gets it. It's not just alphabetical order anymore.
Precisely. You're giving each category its own dimension, its own mathematical space for the model to work with. It's absolutely fundamental stuff.
Okay, technique 2 then. This is about numbers we already have. Sometimes the raw number isn't the best predictor. We need to transform it.
Yeah, this is super important, especially for models that make assumptions about how data is distributed. We're tweaking existing numbers to help the model spot patterns better, maybe making the distribution more normal or handling outliers.
Can you give us some concrete examples, not just adding things up, but real transformations?
Sure. The natural logarithm, log, is probably the most common one you'll see.
Why the log?
Well, think about variables like income or website visits or maybe sales figures. They often have a really skewed distribution, right? A few massive values pull the average way up.
Yeah, the long tail effect.
Exactly.
Yeah.
Applying the log function kind of squashes that range down. It pulls the huge values closer to the rest. This stops those outliers from totally dominating the model's learning process, makes training more stable. Especially important for models sensitive to variance, like key nearest neighbors. Scaling helps there too.
You mentioned other things too, like inverses, ratios.
Oh yeah, calculating the inverse, the reciprocal, 1 over the value. That can work well if the relationship you're trying to model is, say, exponential decay. It can help linearize it for the model.
Okay.
And then there's the feature cross. This is really powerful. You multiply two existing columns together to make a brand new feature.
Like price times quantity to get total sale value.
Perfect example. Total sale value is almost always a much stronger predictor of, say, future buying habits than just price or just quantity on their own.
Because it captures the interaction between them.
Exactly. You've identified an interaction effect. You took two maybe weakly predictive features and combined them into one feature that has a really strong, maybe nonlinear relationship with what you're trying to predict. This is where knowing your business domain really helps figuring out which interactions might be important.
That leads perfectly into technique 3, handling the real messy stuff, text and documents. This is where feature engineering starts bumping into large language models, isn't it?
It really is.
So if you can't just feed a raw 600-page contract into a standard model, how do you get features out of it?
There are a couple of main approaches to distill or structure that information. Approach 1 is summarization.
Okay.
You use a sophisticated text function, maybe even an LLM itself, to generate a dense, concise summary of the whole document. Maybe that 600-page contract becomes a 500-word summary. That summary becomes the feature you feed into your downstream model, not the original monster.
So you keep the core meaning but dramatically cut the noise and the size?
Right. And approach 2 is key feature extraction. Instead of summarizing everything, you use tools, again, potentially LLM-powered agents, to specifically hunt for predefined structured bits of information within the text.
Like pulling out names, dates, dollar amounts.
Exactly. Who signed it? What's the governing law? When does it expire? What's the total value? You're not asking the model to read the whole thing anymore. You're giving it a neat, structured list of facts derived from the document. Those become the features.
Got it. So the main predictive model can just focus on its job, like predicting risk, without getting bogged down in reading comprehension.
That's the idea. Feature engineering is that essential upfront investment. It dictates the maximum possible accuracy and the efficiency of everything else down the line.
Efficiency. Good word. Because once we've got the right features, we need to access them fast and cheaply. Which brings us to section 2, maximizing performance. The 4-stage hierarchy of SQL optimization.
Yes, moving from what the data says to how quickly we can get it.
And query performance isn't just a techie detail anymore, is it? It's strategic.
Absolutely not. Data volumes are exploding. AI and automation need access to massive historical data sets, often in near real time. Slow queries are major bottlenecks.
Impacts decision-making speed, obviously, but also the wallet.
The hidden cost, yeah. It's huge. Every slow query just sits there grinding away, burning CPU, eating RAM in the cloud. That translates directly to your bill. Optimization is fundamentally about cost control and ensuring insights arrive when they're still useful.
Right. If the AI needs data from the last minute and the query takes 60 seconds.
The insight is already stale. Worthless.
So, first things first. Diagnosis. You can't optimize what you don't understand. The main tool here, SQL or even some NoSQL databases, is the explain command.
Explain is non-negotiable. It's like the MRI for your database query. It doesn't actually run the query.
Okay.
It just asks the database optimizer, hey, if I were to run this, how would you do it? And it gives you back the plan, the query plan.
And what does that plan tell us? What are the key pieces of info?
3 main things for every step in the plan. Estimated time for that step, estimated resource cost. The database often calls this just cost, meaning I/O and CPU cycles. And crucially, the number of rows the database thinks it will need to look at, or scan.
Okay, so when we run explain and look at that plan, what are the big red flags? What screams this is slow and expensive?
Number one, by far, a huge difference between the number of rows scanned and the number of rows returned.
Yeah.
Imagine a table with 1 billion rows. The plan says it scanned 950 million of them, just to give you back 10 customer records. That's a massive failure. It means the query isn't targeted at all.
It's doing thousands, maybe millions of times more work than it needs to.
Exactly. Another big warning sign. Lots of sorts showing up in the plan. Sorting is incredibly resource intensive
Why's that?
because the database often has to pull all the relevant data into memory, into RAM, just to arrange it in order for, say, an order by or a group by Y.
Right.
If it doesn't fit in RAM, it spills to disk, which is even slower. It burns time and resources.
And the ultimate performance nightmare.
The full table scan. This means the database has no better option than to literally check every single row in the entire table from start to finish. Eliminating full table scans is basically the holy grail of query optimization.
Okay, diagnosis done via explain.
Oh.
Now we optimize following this 4-stage hierarchy. You said it's ordered by complexity, starting with the easiest, highest impact stuff. Stage 1, query tuning.
Yep. Fix the syntax first. Probably 80% of slow queries are just badly written queries. This requires zero changes to the database structure itself. Just smarter SQL. Always start here.
And the main technique is filtering early, using where.
Absolutely fundamental. You have to tell the database to throw away data it doesn't need as early as possible. If you only want data from this year, put where date. 2024-0101 right at the beginning. Don't wait until after you've done complex joins or aggregations. Filter first.
What about other syntax traps, like joins or in clauses?
Joins need care. Joining huge tables without the right conditions or a non-index columns, disaster. And the in clause, avoid putting massive lists of values in there, like where customer in 1, 2, 3, 10,000. The optimizer often struggles with that.
Is there an alternative?
Often, using exists with a subquery is much better than in. Exist can stop as soon as it finds the first match. In might have to materialize the whole list first. Also, a huge performance killer, putting functions on the left side of your where clause.
What do you mean?
Like if you have an index on transaction date, but you write where year transaction date 2024.
Ah, I see.
The database probably can't use the index effectively because it has to calculate the year for every single row before filtering. You need to rewrite it so the column is on its own, like where transaction date 2024-0101 and transaction date 2025-0101. Then the index works.
And after each little tweak,
Run explain again, every single time. Quantify the impact. Did the cost go down? Did the row estimate change? Did that nasty sort disappear? It's empirical.
Okay, so we've tuned the query syntax within an inch of its life, but it's still too slow. Now we move to physical changes. Stage 2, indexing.
Correct. Indexing is how we fight the full table scan. It's like creating a sorted directory or, well, an index for your data. Think of a phone book versus reading every name on every page.
So instead of reading sequentially, the index lets the database jump straight to the right section.
Exactly. It usually uses something like a B-tree structure. If you're looking for customer ID 500 in a million-row table, instead of checking row 1, row 2, row 3, the index might let it jump to the middle, realize 500 is in the second half, jump to the middle of that, and find it in maybe 3 or 4 steps instead of 500,000. Huge speed up for reads.
Sounds amazing.
Yeah.
Why not just index every single column then? There must be a catch.
Oh, there's definitely a catch. The overhead, the cost. You only want index columns you actually use frequently in your where, order by, or group by clauses.
Why? What's the cost?
Write performance suffers. Every time you insert a new row or update or delete an existing one, the database doesn't just change the table data. It also has to update every single index that includes that row to maintain the sort order.
Ah, so one logical write operation might trigger multiple physical I/O operations behind the scenes to keep all the indexes tidy.
You got it. You trade faster reads for slower writes and more storage space for the indexes themselves. If your table gets tons of writes like logging sensor data, every second over-indexing will absolutely cripple your ingestion rate. Plus, indexes get fragmented over time and need maintenance. It's a balance.
Okay, indexing helps, but maybe the table is just too enormous. Billions of rows. That takes us to stage 3, partitioning, horizontal scaling.
Right. This is a bigger architectural change, usually needs coordination. It happens at the storage level. You take one massive logical table and physically split its data into smaller chunks or partitions based on some key.
Like splitting sales data by month or year.
Exactly. Or IoT data by day or even hour. The table still looks like one table to your application, But underneath, the data is stored in separate physical segments. So if you partition your massive log table by day and you query for show me everything from yesterday.
The database only needs to scan yesterday's partition. It ignores all the others.
Precisely. Instead of scanning billions of rows, it might only scan millions. The performance gain can be astronomical, and resource usage drops dramatically. It only touches the relevant bucket.
And if even that's not enough, or the whole way that data is structured is the problem. Stage 4, data structure and architecture redesign, the last resort.
This is the big one. High effort, high cost involves the whole team. The fundamental idea here is data that's often used together should be stored together. This might mean, brace yourself, denormalization.
Ooh, controversial, adding redundant data back in.
Sometimes, yes.
Yeah.
To avoid super expensive JUIN operations on the fly, maybe move from a perfectly normalized third normal form structure to something like a star schema, which is common in data warehousing. You accept some redundancy for much faster analytical queries.
And what if the sheer volume just overwhelms any single database system?
Then you're looking at fundamentally different architectures. Distributed computing frameworks, things like Apache Spark, Hadoop, or modern massively parallel processing MPP data warehouses like Snowflake or Redshift or BigQuery.
So processing the data across many machines at once.
Exactly, adding parallelism. But that's a whole different ballgame. It changes your tools, your code, your infrastructure. It's the most complex stage.
Okay, wow. So we've transformed the data with feature engineering, and we've optimized access speed with SQL tuning and architecture. But so much useful information isn't in neat tables, it's locked up in documents.
Yeah, vast majority, often.
Yeah.
Emails, PDFs, contracts, reports.
Which brings us neatly to section 3, conquering chaos. Using LLMs and agents for unstructured data.
Yeah, this is where things get really interesting and frankly really challenging. The unstructured data problem. It's huge.
Documents have all this critical info, but they're messy, all different formats, lengths.
Exactly. And the goal here is similar to feature engineering. Take that raw, chaotic document and turn it into structured, actionable data points. Data that can feed the kinds of systems we just talked about optimizing.
And it's not just messy, the complexity is wild. You mentioned documents from short notes to 600-page behemoths and tables that split across pages.
Yeah, that's a classic problem. A financial table starts on page 37, the rest is on page 38. Traditional tools just completely lose the plot there. They can't maintain the context across the page break.
So before LLMs, what was the main tech for this? OCR, optical character recognition.
OCR was revolutionary for just getting text off scan pages. It uses computer vision to recognize characters and turn pixels into, ASCII or Unicode text.
But its limitation is?
It has no semantic understanding. It sees the letters TABLE, but it doesn't know that means a structure with rows and columns, or that one number is a subtotal of others. It struggles massively with layout. It just gives you back a big wall of text, basically. Still needs tons of human effort to structure.
And beyond just extracting from one document, the real value often comes from understanding how documents relate to each other, right? These hierarchies you mentioned.
Absolutely critical. A single document often doesn't tell the whole story. We think about two kinds of relationships. First, vertical hierarchies.
Like a chain of command.
Kind of. Documents that build on each other logically. Think about contracts. You might have a big master services agreement, the MSA, setting overall terms.
Okay.
That leads to a specific statement of work, an SOW, for a particular project. That SOW might generate a purchase order. And finally, that leads to an invoice being sent.
You need the whole chain to understand if that final invoice is valid.
Exactly. You can't validate the SOW without the MSA, can't validate the invoice without the PO and SOW. Then you have horizontal hierarchies.
This is different types of documents related to the same event.
Right. Think about an insurance claim. The claim form itself might reference a shipping receipt, proof of delivery, and also a certificate of insurance, COI. 3 different document types, all linked to the same incident. The system needs to connect those dots.
This all sounds incredibly complex to automate. How did LLMs change the game? What was the breakthrough?
The big shift was foundation models like GPT and other transformers. They started treating language not just as sequences of words, but as a mathematical space.
A mathematical.
Yeah, think about it. English has a huge vocabulary, but it's finite. Maybe 170,000 active words, plus symbols, numbers. LLMs use billions, now trillions of parameters to create this incredibly complex, high-dimensional map of that entire space.
Mapping the words.
Mapping the relationships between words and concepts. Every word, or part of a word, a token, gets turned into a vector, a string of numbers. And the position of that vector in this giant map represents its meaning and its relationship to all the other vectors.
Okay, let's try and peek inside that transformer black box a bit. How does it actually do that mapping? Give us the simplified version.
Okay, super simplified. First, the input text gets chopped up into tokens. These might be whole words or sometimes parts of words.
Step 1, tokenize. Then,
Embedding. This is where the magic starts. Each token is converted into a numerical vector, that list of numbers we talked about. Critically, tokens with similar meanings end up with vectors that are close to each other in this mathematical space. Like king and queen would be relatively close.
got it. Turning words into coordinates on a map? What's next?
The core transformer layers. These take those initial 1D vectors and project them into a much, much higher dimensional space, often represented as a 2D matrix. This lets the model consider the context, how words relate to each other in the sentence, not just in isolation. This is where the famous attention mechanism lives.
Attention, like figuring out which words are most important to understand another word.
Exactly. It weighs the influence of all other words on each specific word. Then you have layers for attention and normalization that refine these relationships, kind of grouping related concepts together within that huge matrix space.
Okay, so it's built this incredibly complex mathematical picture of the text's meaning. How does it generate an output, like an answer or a summary?
That's usually the job of the softmax layer or something similar. It looks at that final mathematical representation and calculates probabilities. What's the most likely next token? It picks the highest probability one, generates it, adds it to the sequence, and repeats.
Generating word by word based on probability.
Essentially, yes. And the final step is projection, turning that chosen mathematical representation back into an actual word or token from the vocabulary that we can read.
Wow. Okay, so that complex process leads to something you said was counterintuitive. Processing a document isn't just shrinking it down, it's expansion, then contraction.
Right. Most people think, I have a 1,000-word document, I want 20 data points out. Easy, just cut out the fluff. But that's not how it works effectively.
It actually gets bigger first.
Massively bigger.
Yeah.
Temporarily. First, you might run high-res OCR. That 1,000 words suddenly becomes potentially millions of data points if you consider pixel data, coordinates, table structures, etc. It's digital noise at this stage.
Okay.
Then sophisticated NLP tools might layer on grammatical analysis, semantic tagging, more expansion, and then the LLM comes in and creates those huge vector embeddings we talked about, mapping all the context, exponential expansion.
So you blow it up to capture absolutely every possible piece of information and relationship.
Yes. You create this incredibly rich, high-dimensional representation. Only after that massive, compute-heavy expansion can the LLM intelligently perform the contraction. It uses its understanding of that huge context map to filter the noise, find the signal, and accurately pull out just those 20 structured data points you actually needed.
Which explains why these models need so much processing power.
Exactly. It's not simple reduction.
So how do people actually implement this? It sounds like a complex pipeline. You mentioned agent-based workflows.
Yeah, agents are becoming the way to orchestrate this. Think of them as specialized microservices or modules, each doing one part of the job. They combine older tech, like really good OCR, with the power of LLMs.
Okay, so what are the key agents in a typical document processing workflow? You start with an inspections agent.
Right. This is like the bouncer at the club. It checks the incoming file. Is the checksum okay? Is it the right file type? Is it corrupted?
Yep.
Basic stuff, but it stops you wasting expensive LLM cycles on garbage files.
Good first step. Then the OCR agent.
This does the heavy lifting of character recognition. Using the best engine for the job might be specialized for invoices or legal text. It turns the image into text and hopefully identifies basic structures like tables, but still without deep understanding.
Then the vectorization agent bridges to the LLM?
Exactly. This agent takes the OCR output, chunks it into tokens the LLM understands, calls the embedding model, and creates those vector representations. This makes the document semantically searchable and understandable for the later stages.
What about messy scans, like someone scanned 20 invoices as one big PDF?
Ah, that's where the splitter agent comes in. It analyzes the document structure, looking for big white spaces, repeating headers, page breaks, and tries to intelligently slice that single file back into the 20 original logical documents. Crucial for context.
Okay, makes sense. Now, the star of the show, the extraction agent, this does the actual pulling of data.
This is where the magic happens for getting structured data out. This agent uses automated prompting, but we're not talking simple prompts like summarize this. No, These are highly specific, often complex prompts, maybe developed over weeks, that basically instruct the LLM to fill in a predefined template or schema, like here's an empty JSON object with fields for invoice 8, vendor ID, total amount, fill it based on the document context.
So it forces the LLM to output structured data.
Precisely. It turns the document's chaos into a clean, predictable data structure ready to be loaded into a database. This is the core contraction step.
And one more, the matching agent. This brings back those hierarchies we discussed.
Yes, after you've extracted data from potentially many documents, the matching agent looks at the extracted features, like PO numbers, dates, names, and the metadata, and figures out the horizontal and vertical relationships. It connects the claim to the shipping receipt and the COI. It links the invoice back to the SOW and the MSA. It builds the full picture,
Creating that holistic context.
which is essential for any downstream AI that needs to make complex decisions based on the whole document swarm around an event, not just one piece of paper.
This agent-based approach, it feels different from traditional data pipelines, which leads to your final outlook, the shift from deterministic workflows to autonomous workflows.
Big shift. A traditional deterministic workflow is rigid, like an assembly line. Input A must go to step B, then step C. If step B chokes on weird data, the whole line stops.
Right. Inflexible.
Autonomous agents change that. They're often event-triggered. An agent wakes up when new data arrives, or when another agent finishes a task relevant to it.
So they don't just follow a fixed sequence.
Exactly. They can interact in non-deterministic ways. Agent A processes a document, realizes it's super complex, and decides itself to route it to a specialized high-power and maybe higher cost parsing agent instead of the default cheap one. The agents can potentially make path decisions based on the data's context.
That sounds much more efficient. Less human hand-holding, better use of resources.
That's the promise. Higher efficiency, better scalability, because resources are used only when triggered by a relevant event. But the really exciting part is that this non-deterministic autonomous approach might let us handle messy, complex edge cases that would just break a rigid pipeline. It unlocks new possibilities.
Okay, that has been a serious deep dive, covered a lot of ground. We started with feature engineering transforming data so models can learn.
A foundation.
Then the 4-stage hierarchy for SQL optimization, making sure we can access that data quickly and affordably.
Speed and cost control.
And finally, these agent-based workflows using LLMs to tackle the chaos of unstructured documents.
Conquering the mess. And the key takeaway really is that none of this is set it and forget it. Optimizing features, queries, workflows, it's a continuous job. You have to keep refining. But mastering these techniques, that's what builds the robust, scalable data foundation you absolutely need for serious AI, especially looking forward. Without it, your amazing model stays a demo. It won't survive the real world's complexity and cost pressures.
That really sets up our final provocative thought for you, our listener. We're moving from these fixed linear data pipelines towards these more autonomous event-triggered agent systems. We're intentionally adding a layer of non-determinism, of agent decision-making into our data infrastructure. So the question is, what happens next? What new kinds of insights, what emergent system capabilities might we unlock when we actually let the intelligent agents figure out the best path rather than forcing everything down a predefined rigid track? Something to think about.